The purpose of this lab experiment was to observe an object moving at constant speed and direction and compare its observed behavior in an experimental approach to a computational model of its motion. The steps of this experiment were to first record a video of an object moving with constant velocity and direction. I chose a mascara tube rolling on a sidewalk. The second step was to analyze the video taken using tracker software to get data on the object's position versus time. Then we used Newton's second law to construct a computational model in Python of the object's motion. And finally, we graphed and compared the data collected from the experiment and the data from the computational model to see the similarities and differences. The results of this experiment showed constant velocity through the linear results of the computational model and similar results from the experimental data, which showed that the object had no acceleration and thus constant velocity. The main concepts in this experiment were Newton's first law, which is that an object in motion or at rest will stay in motion or at rest unless there's a net force acting on it. Newton's second law, which is that F net, or net force, is mass times acceleration, or the derivative of position over time, or dp over dt. The momentum principle, which is the net force times the change in time, equals the mass times the change in velocity. And constant velocity, which is just that when velocity is constant, it is equal to the change in position over the change in time. So the video from the experiment is on the left. It shows the video taken as well as the data recorded in the tracker software. In this experiment, the system is the mascara tube, the sidewalk, and just the earth as a whole, and the surroundings would be like the air and just everything around the system. There are possible sources of error in this experiment, which could come from air resistance, which could make the tube speed down or slow up, friction with the ground, which could affect the velocity of the tube. It could come from human error as well, such as an inconsistent push to the tube in the video, or just error in using the tracker software and reporting the position of the tube in the video. The initial conditions set in the computational model, I set the tube mass to 0.01 kilograms, the average velocity, which I determined by taking 2 data points from the tracker model and subtracting the positions and then dividing that by the change in time. And I determined it to be 0.176 meters per second, and the initial position was the origin. In the computational model, I repeated a while loop and the range and the time was just the duration of the video, so it went from 0 and it repeated until the time was got to 1.385 seconds. Net force was set to 0, and I updated the velocity using the function final velocity is initial velocity plus net force over mass times the change in time. Since the net force is 0, the final velocity was just equal to initial velocity in this case. I updated position using the function position is equal to initial position plus velocity times change in time. And since velocity was constant, position was updated at a uniform interval. So you can see in this graph, the blue line shows the computational data, and the red dots, it's a scatter plot, show the observed data from the video. The computational data is linear because there was no net force on the object, so there was no acceleration, which means that the velocity was constant and the position changed at a constant rate compared to time. The observed data is very similar to the computational data. It doesn't look as much like it on the graph, but you can see on the position side, the intervals in the change in position are very small. So if it were like zoomed out a little more, you could see that the computational data and the observed data are very similar. However, it's not quite linear just because of the sources of error in the experiment, but it's close enough that we can determine that, or we can say that there was no net force on the object, and the object had constant velocity. Yeah. So what if the axes were changed? If the axes were flipped to swap the positive and negative x directions, the sign of the position values would change in the data, but the magnitude would remain the same. This is because it would only affect the orientation of the coordinate system, representing the tube moving towards the negative direction instead of the positive, but with the same magnitude of the velocity. What does this mean? In this experiment, the observations align with the computational model when net force is set equal to 0. This implies that the object experiences an equal number of pushes and pulls, or forces, in opposite directions, which results in a net force of 0. Because all the forces acting on the object cancel out to create this net force of 0, it can't be determined how many forces are actually combining together and acting on the object in this case.